I'm going to talk about threshold secret sharing. I'm Gilad Asharov from Bar-Ilan University. Thank you all for coming. Thank you for the organizers. What is secret sharing? So I assume that most of you are familiar with secret sharing. The agenda for today, so I'm going to talk on Shamir secret sharing. I'm going to focus on threshold secret sharing. But I'm going to talk on other forms of secret sharing as well, just to give you some general knowledge about it. I'm going to also talk about what happens if the parties that receive the shares in the later stage do not participate, they are dishonest, and then what to do where the dealer is itself corrupted. This is going to be in the second hour of the talk. So what is secret sharing? So suppose we have some sensitive information, a secret key for my crypto wallet or some sensitive database, and I want to, it's a common knowledge that you should not put all your eggs in one basket, because if you do this, then this is what usually happens. We want to, we don't want to have a single point of failure. So what we want to do is to split the trust or distribute the secret and keep it in different places. So secret sharing has two phases. The first phase, it's a sharing phase. It might be an algorithm. In a later stage, it might be a protocol. And here we have a dealer that has the secret S, and the dealer computes shares and distributes the shares, and we are going to put each share in different locations. In this case, we usually talk about different parties. I'm going to give one share to one party. And the shares, the privacy requirement is that each share doesn't provide any information about the secret S. And even stronger than that, we want that even subset of shares do not provide information about the secret S. Moreover, the second stage of secret sharing is the reconstruction phase. Here there is no dealer. The parties come together. They want to take all their shares out and to reconstruct the secret S. So we need an algorithm or a protocol that will enable us from the shares themselves to reconstruct the secret S. So let's look at an example. To share a secret S among n parties, so let's say my secret S is 128 bits secret, say n over 4. And it's a secret key. So the first idea that comes to mind is to let's split the secret into pieces, 4 pieces in this example, and give each party the first part of the key, the second party, the second part of the key, and so on. Is that a good or bad idea? Let's see. So the question is, what does each party know about the key? What do I learn about the key when I see my share? I learn 32 bits of the key, which means that it's not the greatest idea. And what do 3 parties know about the secret? They know almost all of it. They know 96 bits of the key. So this is not the best idea, and we want to do better. We want to have that single piece of information, or even 3 pieces, do not give us any information about the secret. So a better idea is the following. So in order to share a secret S, what we are going to do, we are going to pick at random 3 values, S1 to S3, in our domain, which is keys of size 128 bits. And then we're going to set S4, the last piece, as S minus the sum of the first 3. Okay? Now I'm going to give each party a share. In the reconstruction, all we have to do is, given all the shares, in order to reconstruct the secret, we just have to sum up modulo 102 to the 128. And now I ask you exactly the same question. What do 3 parties know about the secret? And the answer is nothing. All they got, all their view, It's just 3 random values. They don't know anything about the secret. So before we proceed, I want to introduce some notation. So let's, S is going to be the domain of the secret. It's where the secret is coming from. In our example that we just saw, it was 128 bits. N is the number of parties. And we are going to have a threshold. What is a threshold? So we'll have a secret sharing in which T plus 1 parties can reconstruct the secret. They can learn everything about the secret. But T parties cannot learn anything about the secret. And this is, corresponds to what is called in the literature as T plus 1 out of N secret sharing. Note that I'm using T as the privacy and not as how much you can reconstruct, how many parties you need in order to reconstruct. In a secret sharing scheme, as we say, this has two algorithms or protocols, sharing and reconstruction. We want it to be computable, polynomial in the number of parties, and logarithmic in the size, in the space of the secrets. And let's see just the syntax and requirements. So the sharing algorithm, it receives the secret, has some randomness, and it outputs some shares, where SI is going to be the share of the ith party. And the reconstruction, we want that when we get sufficient enough, like when we have an authorized subset that can reconstruct the secret, if we give all those shares together, we pull them together, we can actually retrieve the secret, where for correctness, now the requirements, so we have correctness. Correctness is that every subset of parties, authorized set, can actually reconstruct the secret. So sharing of S, I distribute into shares, then we come to reconstruct, we have enough T plus 1 parties will be able to reconstruct. And we want also to have privacy or T privacy. So the distribution of any T shares is independent of the secret S. Formally, we want that for every pair of secrets, S and S prime, and every subset of less than or at most T parties, the distribution of shares when we start the sharing from, we share S, we get all the shares, and then give to this corrupted set, or the view of the adversary that corrupts at most T parties, we give it that shares versus when we start by sharing S prime and give the adversary those set of shares. Okay, so these two supposed to be the same distribution. So we cannot learn from my shares, from T shares, I cannot learn what secrets was distributed. Okay? So we already saw N out of N secret sharing. I just want to formalize it in the same syntax that we just described. So assume that S is some group and we have an operation of addition. For example, S can be ZM. And the sharing algorithm, just we chose S1 to S N minus 1, uniformly and independently at random. We set the last share to be S minus the sum of all previous, and then each party receives 1 share. In order to reconstruct, we need all parties to be there, and therefore reconstruction is also easy. We just need to take all the shares, sum them up, modulo, sum them up in our group, and then reconstruct the share, the secret. Okay? Now I ask you, how efficient is this scheme? So what is the size of each share? So essentially, it's the size, is the number of bits to represent a field, an element in our group, which means it's exactly the size of the secret. It's essentially comparable to the secret. Okay, how to deal with general threshold with T that is not N, okay, when threshold that is less than N. So one option, one idea, is doing the following. So for every authorized subset that is big enough, we're going to share T plus 1 out of T plus 1 secret sharing scheme. We're going to share S among that subset. Okay? This will able to reconstruct because any authorized subset of parties will be able to reconstruct S. But the problem with this, this scheme, first of all, is that a secure scheme. Yes, like every subset of parties that is at most T cannot learn the secret. The problem with this scheme is its efficiency. Each party receives essentially n choose T plus 1 shares of size S each. And this means that it's exponential in the number of parties when T is roughly n over 2 or something, some constant of n. Okay, so we want to do something which is better. And here we come to Shamir secret sharing. So for Shamir secret sharing, we need something a bit richer than a group. We need a field. A field is just that we have two operations. We have additions and multiplication. And I'm going to denote the field as F. And I say that the set of all possible secrets is exactly F. I assume that the number of elements in the field is greater than the number of parties. And I just fix some n distinct constants that are non-zero in the field. So how Shamir's secret sharing looks like. So in order to share S, what I'm going to do, I'm going to pick a random degree T polynomial with S as its constant term. So Px is a polynomial where I'm going to plant S as its constant term, and I'm going to choose P1 to Pt uniformly at random from the field. These are going to be random values, random elements. And then party Pi, the share of party Pi is going to be just the evaluation of the polynomial on some specific point. So each party has some specific alpha, and according to its point, I'm going to evaluate the polynomial on that point, and this is going to be the share of the party Pi. What's going on? So the properties here is that every set of T plus 1 participants can recover the secret. We're going to see it in a few minutes. Moreover, every T shares do not reveal any information about S. And what is important in terms of efficiency is now that my share is a single value. I don't need to receive exponentially many shares, many values. It's just one piece of secret, piece of share that contain all information can satisfy all subsets. So how to reconstruct, or what is the idea behind Shamir? So we know that any two distinct points determine exactly 1 degree 1 polynomial. Moreover, every 3 points determine exactly 1 degree 2 polynomial. And in general, every T plus 1 points determines exactly 1 degree T polynomial. So if the dealer chooses a polynomial, gives the n parties points on that polynomial, from T plus 1, we can reconstruct the polynomial, and then we can retrieve the secret, which is the constant term of that polynomial. How to reconstruct? So I say that we can reconstruct the polynomial. How do we do that? So let's look at the actual way to reconstruct. So let's say I have T plus 1 points on a polynomial, and your goal is to actually find that polynomial. How to do that? So let's take a look on this f1x, this polynomial. Okay? I'm going to describe an algorithm that reconstructs the secret. Reconstruct the polynomial. So this polynomial, we're going to put y1 here, 1 point, and then we're going to multiply in all those terms. And what is so special about this polynomial? I ask you, first of all, what is the degree of that f1? What's the degree of f1? T. It's exactly t. We have x exactly t times. The degree is t. Moreover, what is f1 on the point alpha 1? It's exactly y1, because once I put here alpha 1, this cancel out, everything cancels, it's all 1, and we are left with only y1. So this polynomial, when we evaluate it on alpha 1, we get exactly y1. What about f1 on alpha 2? This time is going to be 0, because if I put here alpha 2, sorry, this is going to be 0, and it's multiplication, everything is 0. And this is the same for any other point. So we found a polynomial that when we evaluate on alpha 1, we get exactly y1. We can continue on the same way and define f2 of x exactly the same way. We put y2 and multiply in the other terms. So we found t plus 1 polynomials that on every point are evaluated exactly on one of them and 0 otherwise. So if we look at the sum of all these polynomials, it's going to be a polynomial of degree t, where in each point it's going to be evaluated exactly to the right polynomial. And now I ask you to prove that this sum is actually p of x that we wanted. So how do we prove that? So f of x is a degree t polynomial, and it's been evaluated on all the right points as we wanted. Now we claim that this is the right polynomial. There's no other polynomial. And this is true because if we look at fx minus px, where p is the polynomial that the dealer used and f is the polynomial that was reconstructed, so fx and px, if we assume that they are not the same, then it's going to be a non-zero degree t polynomial that has on exactly all the alpha 1s to alpha t plus 1, it's going to be evaluated to 0. So this polynomial has t plus 1 roots, and therefore it's impossible, so it must be that f of x equals p of x. Okay. Why is that Shamir secure? What's the intuition? So we all know that, so why my share doesn't reveal any information about the secret? I got a point on a polynomial that the dealer chose. Why it doesn't reveal any information? So let's look at t out of 2 secret sharing, which corresponds to polynomial of degree 1. And I got 1 point on that polynomial. Why I don't know the secret? So I want to show that every secret is still possible. So it might be that this is the secret, and this was the polynomial that the dealer chose. Or it might be that this is the secret, and this is the polynomial that the dealer chose. And in fact, all possibilities, we have all possibilities. For every secret, we might have this is the line. And now when I have only one point, I cannot know which secret was it. Only when I get the second point, I can see that this was the line, and this is the secret, and not this one. Okay? Another example. So now we have a dealer that 3 out of 4 secret sharing, the polynomial has degree 2, and I get 2 points on that polynomial, and I'm asking what is the secret. So it might be that this is the secret, it might be that this is the secret, we don't know. And in fact, only when I get the 3rd point, I am able to reconstruct the polynomial and see that this was the right one and not this one. Okay? So let's formalize it. I'm going to denote by PST the set of all polynomials over F over the field with degree T and constant term S. The size of all possible polynomials is exactly F to the T, because we have to choose T coefficients. The secret key, the constant term is the secret. We cannot play with that coefficient. So we can present the sharing algorithm as just choosing a random polynomial P of X from the set of all polynomials and just evaluate it on alpha 1 to alpha n. The security formally, so every T shares, the claim is that every T shares are distributed uniformly at random in F. How do we prove that? So we show that every fixing of points, every point in the field, every T values, and every subset of the parties, there is a possibility that the sharing algorithm, that my shares will collide with that values. And not only that there is possibility, it's going to happen with exactly the same probability for every T point. So, and why is that? It's exactly the reconstruction algorithm again. So exists exactly one polynomial P of X in which its constant term is the secret, and it goes through each one of the points that I fixed. What's the probability that sharing will choose that polynomial? Is exactly 1 over F to the T. This is true if my secret is S or if my secret is S prime. It's exactly the same calculation. I get exactly 1 over F to the T. So for any two secrets, S and S prime, the probability that my T shares that I saw correspond to this secret or that secret are the same, and it's 1 over F to the T. Okay? So I want to give two applications. One is key recovery. So we know that it's a little bit hard to remember a secret key. Now application, where to use secret sharing. So instead of remembering the actual key, I'm going to remember a passport P and store H of P, where H is some random function, hash function, XOR K. Okay? And then I have to remember the password, and I can recover the key. But what happens if I forget the password? Then I'm in the same problem, right? So instead, let's use 3 out of 5 secret sharing, and I'm going to share the key using to get 5 shares. And I'm going to select some personal questions in which the user will know the answers A1 to A5. I'm going to store H A1 XOR S1 to H5 A5 XOR S5. And once I know, it's enough to remember 3 out of the 5 personal questions, and I can recover the secret key. Another application is robust combiner. Say that we have 3 encryption schemes, pi1, pi2, pi3, and I don't know which one of them is actually secure. It might be that some of them are broken. So I want to get one encryption scheme that is at least as strong as the best one of them. So how we can construct a new scheme that is secure if and only if at least one of pi1, pi2, pi3 are secure. The idea is that when we take the encryption scheme, we are going to share, when I want to encrypt, I'm going to take M, and I'm going to use secret sharing to get 3 different messages, M1, M2, and 3, and then I'm going to encrypt each one of the messages using a different scheme. Why the message is protected? So even if 2 encryption schemes are broken, you can get only 2 shares of the message, you still cannot recover the message. It's enough that one of the three is secure, and then you get security. Okay, I'm going to talk about other notions of secret sharing. The first one, it's not others, but some notions of secret sharing. First one is linear secret sharing. So in linear secret sharing, the secret is an element in the field. The randomness of sharing is a vector of random elements in the field. And to share, the share of each party is some vector, where each one of its coordinates is some fixed linear combination of the secret and the randomness. And I'm asking you, okay, is that clear? Its definition, look at it one more second. I'm asking you whether or not Shamir secret sharing is a linear secret sharing scheme. So can we represent Shamir secret sharing as the secret is an element in the field, the randomness of sharing is a vector of random elements in this field, and then the share of each party, it's a vector. In Shamir is actually one value, where this value is some fixed linear combination of the secret and the randomness of the sharing algorithm. So Shamir satisfies that or not? So let's take a look. So it's a different view on Shamir secret sharing. Just let's look at the matrix view of Shamir. So I'm going to put S as my secret. That's going to be, I'm going to look at the vector where S is the first coordinate, and then the randomness, which is the other coefficients, are the next t coefficients, t points on this vector. And if we have n that it's much greater than t, then we're going to have zeros at the end. If t equals n minus 1, then we don't. Yeah. Okay. So pretend that you see that vector here, and you multiply that vector. It's the conversion between slides. So we take that vector and we multiply by this matrix. What is that matrix? It's going to be 1, alpha 1, alpha 1, 2, and so on. And you multiply that matrix with this vector. Now, you need some imagination, I know. Okay? And what do you get? So you get exactly the valuation of the polynomial on each one of these points. You see it? Right? Okay? We get exactly the valuation of the polynomial on each one of these points. Now there's supposed to be another one. Okay. So what is nice about this matrix is the van der Monde matrix. It was supposed to be on the bottom of the slide. And this matrix has an inverse if and only if all the alphas are different, they're distinct. And so what does it mean? That if we take here V alpha times P, what we are going to do, V alpha is going to be the van der Monde, P is that vector that we saw S, P1 to P2, Pt, and then zeros. So this matrix times P going to be all the evaluations. This metric has an inverse, and therefore we can represent P as the inverse of the van der Monde times the shares that the parties receive. How this inverse of the van der Monde looks like, okay. I'll do it on the board. Okay, so what's going on is that if we look at the van der Monde minus 1, we're going to multiply that with all the points. And what we are going to get is exactly S P1 to Pt and then zeros, right? This is what is written in the second line. But the van der Monde number to the inverse is just, let's just look at the first line. So there are n values, some lambda 1 to lambda n, and when we multiply that with all the points, we're going to get exactly the secret. Okay? So we can represent the secret as a linear combination of all the points. This is what's supposed to be in this line. So Shamir is a linear secret sharing scheme. Okay, we can represent this sharing as a linear combination. Each share of each part is a linear combination of the secret and the randomness. And just two notions that I want to mention, and we are not going to focus on. So this is equivalent to monotone span programs, which is a linear algebraic model of computation. And there is also the notion of packed secret sharing, where the shares in Shamir, and what we saw so far, each share hides one secret. Can we hide more than one secret using our shares? Think how to do it for a second, and then I'll tell you. So the way to do it is to just plant the secrets on the polynomial in different places. You have to play with the threshold now, but this is also possible. Okay, so so far we had threshold access structure. We have threshold scheme, Shamir. I want to also introduce general access structures. So here we are asking who is actually authorized to reconstruct the secret. Shamir is a threshold scheme in the sense that an authorized set are all the subsets of cardinality t plus 1. For instance, if n equals 4, then all the subsets of two parties are authorized. We have 1, 2, 1, 3. All those subsets are authorized to reconstruct the secret. What about 1, 2, 3? Is that authorized party, authorized subset? Yes, they can even reconstruct in multiple ways. 2, 3, 4 also. And the question is, what happens if our authorized sets are not just according to subset, according to cardinality of the set that comes to the reconstruction? What about more general structures where we have, let's say, P1, P2, and P4 come together? We want to have a secret sharing where only if P1, P2, and P4 come together, or P1, P3, P4 come together, or P2 and P3, they will be able to reconstruct the secret. And for instance, P1 and P3 will not be able to reconstruct. Okay, we want to have a more general access structure. So as I hinted before, access structures are, we have to support only monotone access structures in the sense that if a subset is authorized and A is a subset of some other subset, then B is also authorized. Okay? So how can we satisfy just general access structures? So let's look at this example. 1 to 4, 1, 3, 4, 2, and 3. I can represent it as a CNF. This is what I did already in the previous slide. I said either P1, P2, and P4 can reconstruct, or P1, P3, P4, and so on. And for each one of them, each one of these subsets, I'm going to have a different secret sharing scheme. I'm going to have a different instance of secret sharing. I'm just going to share S among these three parties, among these three, and among that two, and then give each one of the parties all the shares that it actually is about to receive from this construction. Okay? So why P1, P2, and P4 can reconstruct? So I just take A1, A2, and A4. What about P1 and P3? P1 and P3 cannot because A1, they cannot reconstruct from here because they don't know A2. Here they cannot reconstruct because they don't know P1 and P3 do not know B4. And here they cannot reconstruct because they don't know C2. Okay? So each one of these terms is protected, and P1, P2 just is not an authorized set. They cannot reconstruct the secret. Okay. Some additional topics, general access structure. So let's see. So we saw another scheme for constructing secret sharing is this one. And if I'm now using this scheme for an access structure which is the threshold access structure. So what is going to be the size of the shares in that scheme? Okay, how many shares each party receives? It's exactly the number of subsets, authorized subsets that it appears. So as you can see, in Shamir's scheme, we said we have only one. Here we are going to have n over t if we are using the threshold access structure. And the fundamental question that we have, so there is a huge gap. And the fundamental question is, what is the optimal share size for a given access structure? What is the best that we can have? So for threshold access structure, we can have very efficient construction. Generally, we are in 2 to the n, in the worst case. Where is the actual, what can we do? So for instance, I give you as an exercise, let's say what we saw that every general access structure is possible, but sometimes, because we actually look at like the truth table of all possible values, but sometimes you are given the access structure, we can represent the access structure more efficiently. Let's say that I give you a circuit that I represent the access structure as a circuit that contains n and or gates, and the circuits you evaluate it on a set, and it outputs 1 if and only if this subset S is an authorized set. So C and F can be represented as a depth 2 circuit, but more general circuits, what can we say, can we do better than the C and F construction? Okay, so what's next? I'm going to talk now about 2 other cases. One, I'm going back to Shamir, to threshold schemes, and now we are looking at the reconstruction stage, and we are asking what happens if one party doesn't actually provide the share it was given by the dealer, it gives to the other parties a wrong share. And how many wrong shares can we actually tolerate? How can we correct these shares? How can we actually reconstruct the secret, the true secret? Another thing that we'll do in the next hour is going to be what happens if the dealer itself is corrupted and it doesn't really share a secret. I mean, the shares do not really lie on a degree T polynomial. It does some it manipulates the shares such that when the parties come to reconstruct, they don't have enough information to reconstruct. So T plus 1 was supposed to be able, T plus 1 parties were supposed to be able to reconstruct, but because the dealer is corrupted and the shares do not lie on the degree T polynomial, they cannot reconstruct. So how can we tolerate that? How can the honest parties actually detect if the shares that they received actually lie on the same degree T polynomial? Okay, so in the next 20 minutes that I have, how to deal with wrong shares in reconstruction. This is also called robust secret sharing. So let's start with the warm-up. in the computational setting, and I put an alarm over here because I know that we are in information theoretic settings, so don't, nope, no one will be too mad. So consider what is the setting. So we have T+1 out of n secret sharing. At most, T parties are corrupted, and we assume that the dealer now is honest. It provides the correct shares. The problem is the reconstruction. Parties provide wrong shares, wrong pieces. So the difficulty is when corrupted parties might send in the reconstruction shares that they were not supposed to send. They are different than what they receive. So how can you do it in the computational setting as a warm-up? How can you see, I got a share, I then, in a later stage, I have to reveal it to others. How can you see if the share was correct or not? Sign, right. So just the dealer can sign on each one of its shares, and in the reconstructions, party can verify whether the share that is now being broadcasted or sent to them, it actually has the right signature. If it doesn't, they just remove that share and they know that this guy was provide wrong shares. Do we really need signatures? So again, what is the game? Dealer provides a share to PI, SI, and then in a later stage, when PI wants to, we are in the reconstruction, PI sends SI prime to PJ, and PJ is one to verify whether SI, that this is the value that PI received in the sharing stage, is the same value as it receives in the reconstruction, that PI sends to him later. This is what we want to verify. Do we really need signatures? Okay? We don't, because all we need is to just authenticate some information that's provided by the dealer, and it's in fact, it's enough to use MAC. So I'm going, what is MAC? It's a message authentication code. It's a triplet of algorithms, Gen, MAC, and verify. MAC construct the key. Gen construct the key. MAC, a key with a message. I'm getting a tag that later on only a message and a tag, I can verify that the tag corresponds to the message. If I'm trying to manipulate the tag, it's really hard to do it. In what we will use one-time message authentication MAC. And this is the security experiment. So the key is generated by Gen. The adversary outputs one message of his choice, M prime, and receives one tag on that message. And the difficulty, or what we are trying to capture, we are saying that it cannot output another pair of message and a tag that verifies where it's not the actual message that it already knows its tag. Okay? So this is the security property of one-time MAC. How do we reconstruct one-time MAC? So Gen is going to choose two elements, A and B, in the field. And MAC is going to evaluate the tag as follows, just computes A times M plus B. Okay? In order to verify the message and the tag, I just run MAC again and check that the tag is correct. Security, so why is that secure? Why it's hard to forge the tag on a different message? Okay, so what do we have here? We actually have a line, okay, A and B. What the dealer chose here, not the dealer, the Gen chose is actually a line. And then we are going to evaluate the line. What the adversary sees is one point of its choice. Choose whatever point you want. And you see one point on that line. Now I'm asking you, can you find another point on the same line? Okay? And this is exactly like in secret sharing. You cannot do it. Exactly as in Shamir, you cannot find another share from the shares that I have. So the adversary sees a pair of M prime, T prime of its choice, and it cannot find another point on that line. So its probability to win, to forge a tag on a different message, is 1 over F. It's just to guess a random point in the field. And if we assume that F is big, is exponential, that this is an exponentially small probability. So robust secret sharing, the first idea is the dealer will provide each party, together with its shares, also a tag that it will use to convince other party about the correctness of its own share, and to give to that other party, PJ, the key to verify that MAC. Okay? And in the later stage, when we actually do the reconstruction, PI provides to PJ not only its secret, but only the tag that it received from the dealer. Now PJ wants to verify whether PI provides true information, so I'm going to accept this share if and only if the MAC actually is correct, it verifies. So what do we have so far? So we know that the dealer can provide extra information to aid verification in the computational setting. This was with signatures. In information theoretic settings, we also show that the dealer can provide some extra information to aid their verification. We can see which shares were incorrect. And can we do better? So the question is, can we recognize the wrong shares without extra information from the dealer, or can we even detect and correct errors with 0 probability of failure? So the scheme that we just saw, the dealer had to provide more information, and also the reconstruction has some error if the adversary can somehow find a tag and forge a tag. Now we want a scheme that has 0 probability of failure. And the answer is yes, we can do better using error correcting codes. So what is error correction? We are going back to the problem of error correction. So we have 2 parties, A and B. A wants to send a message to B, but we have a noisy channel, and the channel might flip some points, some elements, the message, can change the message on the way. It doesn't do it adversarially, just flips some point with some probability. So this is a noisy channel. And error correcting codes come to help us to have a reliable communication over a noisy channel. So we have 2 algorithms, encode and decode. In order we come and encode a message, we get a larger message, and then the decoding algorithm gives us back to the original message. And more than that, even if the message, there are some new errors that come along the line because of the noisy channel, the decoding algorithm also gives us the right message. So we can correct some errors that happen. How many errors can we actually correct? So let's take a look. So the encoding function takes a message of size t plus 1, and it's going to add some redundancy to a message of size n. And if I look at the space of sigma to the n, where sigma is the alphabet, C, which is the actual code, is all the points that there is some message that is being encoded to them. So it's going to be very sparse at the end. The code words in the message, in the space sigma to the n, is very sparse. It's only sigma to the t plus 1, where the entire space is sigma to the n. The distance of the code is defined to be the minimum distance between all pairs of code words. And then if we send a message, we enlarged it, there was some error, and what we received is this message instead of that message. The guarantee of error correcting codes is that all the words that are not so far from a code word can be corrected. And in particular, we can decode d-1/2 error. So if an error was introduced, as long as it's not too much, we're going to decode to the closest code word, and the decoding function takes sigma to the n and gives us back into the code word, into the message, or it might say abort. Now, a code word, a code that is being used in error correction, a very important error correcting code, is a Reed-Solomon code. And its encoding algorithm is as follows. We have our alphabet is a field. We are going to fix some points on the field that are going to be distinct. And in order to encode a message of size t plus 1, we are just going to look at this message as a polynomial, and are going to evaluate this polynomial on n different points. Okay? So I have a message of size t plus 1. I'm going to enlarge it to a message of size n by looking at the message as a polynomial and evaluating it on different points. What is the minimum distance of this code? Okay? 2 evaluations of polynomials, 2 different polynomials were evaluated to on n different points. How many coordinates they might be equal at the most. So two distinct polynomials of degree t, let's give them names, p and q, on how many points they might agree on. So the answer is at most t. And why is that? So let's look at the polynomial, which is the minus of the 2 polynomials. It's also a degree 2 polynomial, and it has at most, it equals to 0, at most t points. So Reed-Solomon code is actually n t plus 1, n minus t code. This is the distance, okay? And we take a message of size t plus 1, we enlarge it to size n, and the distance between 2 code words is n minus t. This means that we can correct n minus t minus 1 over 2 errors. So Reed-Solomon code is exactly as you saw, it's secret sharing, right? It's exactly the same. What does it mean? That if we set n to be at least 3t plus 1, what we get is 3t plus 1, t plus 1, and this is the distance. So t parties do not learn anything about the secret. If I'm going to now look at the shares, I'm going to see the shares of all parties as a code word. T parties do not learn anything about the secret, and even if T parties manipulate and change their shares in the reconstruction, we can tolerate d minus 1 over t wrong shares during the reconstruction. Okay, we can correct the code. What does it mean? That the 2t plus 1 honest parties can reconstruct the secret, and again, we are assuming here an honest dealer. The question is how to actually do this reconstruction. And here we are going back into error correcting codes and actually see how to do decoding in Reed-Solomon code. So given n shares that were received, some of them, the dealer distributed, everything was correct. Everything was correct by the dealer, but then the reconstruction, some parties provide wrong shares. How can we recognize now we are the honest parties and the threshold is less than n over 3? We can correct the code. We can correct the wrong shares. And one option is just let's try all the t plus 1 possibilities, all all the t possibility of the wrong shares. However, this is not an efficient algorithm. It will work, but it's not an efficient algorithm. Okay? A better way is to use the decoding of the Reed-Solomon code. Here, the task is as follows. We have n points on a polynomial where at least 2t plus 1 are correct, are lie on the same polynomial of degree t, and t y's are incorrect. And our goal is to find that polynomial p of x. How do we do that? So the idea is to find a polynomial e which has degree at most t, for which this equation will hold. For every point, every alpha that we have in the input, this equation will hold. So p is our polynomial, e is the polynomial that we are looking for, and y's are the points that we received. In the reconstructions, some might be corrupted. Okay? Some might be wrong. So how is that equation even possible? It's possible only if on every point for which is wrong, e is going to be evaluated to 0. On every point which is correct, e is going to be evaluated to something which is different than 0. Okay? So our goal is to find this polynomial e. In fact, the algorithm finds two polynomials. One is q, which is of degree 2t, which is going to be this product. And another one is of degree t, which is this arrow polynomial. So we're going to find two polynomials, one degree 2t, which is this product, and one is e. And then once we have e and q, the algorithm just outputs p as we divide q by e. Okay? So this is the algorithm. The question is how to find q and how to find e. And the answer is just linear equations. So we have 3t plus 1 equations of the form for every alpha, okay, for every point. We have 3t plus 1 equations where, remember, we have yi times e alpha I equals p times equals q, okay? Equals q on alpha. So yi times the arrow polynomial minus, that's the q polynomial. So we have, how many unknowns we have in this 3t plus 1 equations? So what are our unknowns? What are the unknowns first? Is E0, E1 to ET minus 1. We're going to set ET as 1. And all the Q's, Q0 to Q2T. Okay, these are the unknowns. So we have in 2T plus 1 unknowns here, and T unknowns over here. So we have 3T plus 1 unknowns, and we have 3T plus 1 equations. Okay? And just have to solve it. And we know how to solve it. We know linear algebra. So let's look at an example. Let's look at Reed-Solomon code with n equals 7, t is 3, and this is our field. And you are given these points. Now I tell you that 4 of them lie on the same polynomial, and 2 are errors. And I tell you 5 of them on the same polynomial, 2 are errors. Find the message m. Okay, and you can use this thing, this equation. This is how it looks like. Okay, so just these are all the unknowns, E0 to Q4. And let's see on the first equation. So what do we have here? So y1 is 0, 0, 1, and the alpha of the first one is 0. So we have this is 1, this is 0, all of those are zeros. So we have 1 here, This is -1 because we are working in 299. So it's 298. So this is the first equation, equals alpha I squared. We said alpha is 0. And so on and so forth. You can write all these equations. It's going to have a solution. This is the solution, which means that this is E, this is Q. What does it mean? What E tells you where the wrong elements are, where the wrong points are. So E on 0 gives us E on 0 gives you something that's different than 0. E on 1 gives us this is -5. So it's -2 and it's 2 and 3. So in 2 and 3, E of 2 and E of 2 and E of 3, these are the two incorrect points. Okay? And then in order to actually construct the polynomial, all you do is Q divided by E, and you get the polynomial. Okay, so what we saw is that if T is less than n over 3, you can reconstruct the, and parties provide wrong shares, wrong pieces in the reconstruction. We can still reconstruct with 0 error probability, and we can eliminate all errors. After the break, we are going to deal with the case of a corrupted dealer, and we're going to talk on verifiable secret sharing. Thank you.